Good afternoon, everyone. I'm Dave Tilbrook from the Department of Fundamental and Theoretical Physics at Australian National University, and welcome to another seminar. These seminars have now been operating for several years, as you might know, on behalf of the Theoretical Physics Group of the AIP. One of our principal motivations in setting up this series of seminars was to enable Australian physicists to keep up to date with what's going on around Australia and also what's going on overseas, which is important to Australian theoretical physics, and to hopefully encourage collaboration between physicists in different universities around Australia. So the Theoretical Physics Group is one of the topical groups of the Australian Institute of Physics. And you are, of course, most welcome to join. We'd encourage you. We'd love it if you could join. You can do that simply by logging into your membership portal on the AIP website. You'll see the Theoretical Physics Group name under topical groups in your membership profile section. And it's free, of course. And in doing so, it will enable you to keep up to date with significant events that are happening in theoretical physics around Australia. Today's speaker is Professor Archil Kobakhidze from the University of Sydney. He obtained his PhD in 1997 and has since held postdoctoral positions at the University of Helsinki, the University of North Carolina at Chapel Hill, and the University of Melbourne before joining Sydney University. He was awarded an ARC Future Fellowship in 2012 and is a founder of the Theoretical Physics Group at the University of Sydney. As you would have seen from Archil's abstract, his talk today deals with matters related to supersymmetry and the vacuum of general relativity. As we all know, one of the big challenges of theoretical physics today is to understand gravitation from a quantum mechanical or quantum field theoretical point of view. And as Archil pointed out in his abstract, part of the problem for making theoretical predictions that can be verified by experiment is the weakness of the gravitational field for microscopic systems. In this seminar, Archil is addressing this limitation, I think, by considering the global topological features of the vacuum state of quantum systems rather than to restrict the analysis to only local interactions. So just a bit of background for people who might not be aware, this whole business of the interplay between quantum mechanics, topology, and gauge fields in general is a really rich area of theoretical physics, which I think originated as an extension of Yang-Mills theory, introduced back in the mid-1950s, if I recall. But I don't think it was until 20 years later, mid-1970s, that some of the implications of this generalization started to become recognized, such as predictions of instanton solutions, topological sectors, and the introduction of the so-called theta vacuum structure. I'm not sure if Archil is going to talk about that. These had all sorts of implications for the relationship between gauge field theories and topological properties, some of which were very surprising. So to tell us a lot more about this very rich area of theoretical physics and how it might be applied to both the understanding of quantum gravity and also to the task of making potentially experimentally verifiable predictions, Archil's talk today is entitled Topology of Vacuum States, Quantum Gravity and Particle Physics. Thanks, Archil. Over to you.
Thank you, David, for the introduction. Let me share my slides. But first, I want to thank Mari, David, and other members of the theoretical physics group from program committee for running this very interesting series of webinars. And of course, for opportunity to extended to me to give today's talk. Okay, so all right, I hope you see my slides well, and
yep, so it's good.
It's all good. Yeah, thank you. And yes, as David said, I will be talking about today about some thoughts and work we have done at University of Sydney with my colleagues and students in the past 5 years. And most importantly, I will focus in this talk on the work done very recently this year in collaboration with Guy Advali from MPI Munich and Ottari Sakalashvili, who is a research fellow here at University of Sydney. So the key question, which of course we were interested to answer, is very simple. At the same time, is complicated technically and conceptually. So the simplicity of the question is that: are there any quantum gravity effects which are relevant for particle physics? And the relevant means that we can verify those effects, at least indirectly, in particle physics experiments with current technologies. So this is not the first time this question is asked. Of course, there are preceding works, shown here. But the generic consensus is that the quantum gravity effects are too small to be detected within using the current technologies, right? So, and when this statement is made, usually people think about probing the quantum gravity effects using the local interactions. So the local interactions to reveal the quantum gravity effects, the local interactions has to be resolved at the scales of order 10 to minus 33 centimeter, which is a Planck scale. And it is 16 orders of magnitude smaller scales than we can currently probe at the Large Hadron Collider. So that's a basic problem. But what I will try to convince you that there are effects of quantum gravity which manifest through the global properties of the theory, and the particular global properties or topological properties of the ground state, the vacuum state of the systems. Okay, and so that's a key message is the following: that the topological properties of vacuum states engage theories in general. David mentioned theta vacua, and that will be the big part of my discussion here. Including gravity, as you know, you can consider GR, general relativity, as a gauge theory of the diffeomorphism group of general coordinate transformation, lead to a non-conservation of classical conserved charges. This is known as a quantum anomaly, and the emergence of non-perturbative interactions and the fact that could violate the combined CP parity symmetry. Now, this is a known thing. What is not very well regarded is the following: that if you have such a non-conserved charges or conserved quantities, then these explicit violation of charges in certain processes also accompanied by so-called spontaneous symmetry of the associated symmetries. Okay, so I'll try to argue this, and this will be one of the generic takeaway messages of this talk. And spontaneous symmetry breaking occurs through the vacuum condensates, and you can argue that it has intrinsically topological origin. Now, you of course know if there is a spontaneous symmetry breaking in relativistic systems, you always have the accompanied particle state, which is known as a Goldstone states. Okay. So this is very generic statement, and it comes from the analysis of consistency of ground states of the gauge theories, including gravitational theory. Now you can apply this to the standard model of strong, weak, and electromagnetic interactions. So in this talk, the claim in the previous slide is a very generic, as I said. However, I will only concentrate on the theories which are well established within experimentally. That is a standard model of particle physics and general relativity, Einstein's general relativity. So I won't be discussing any speculative theories which go beyond this, although the phenomena may apply to those theories as well. So if I concentrate on the standard model, then the claim is that we predict a new Goldstone particle, which we call the electroweak eta, eta W, which is associated with the spontaneous breaking of anomalous B plus L symmetry. So in the electroweak sector, so B plus L refers to the baryon plus lepton number. Okay. Now, there are other implications of the general phenomena, which I unfortunately won't discuss that much. In particular, if we are looking at the strong sector of the standard model, then for the strong interactions to solve the so-called strong CP problem requires introduction of additional companion axion particle. So that's again requires some additional states. And the interesting fact is that if we combine the effects of quantum gravity or the vacua of usual Maxwell's electrodynamics, then we can explain, in fact, the observed quantization of electric charges, which otherwise cannot be explained within the standard model. So these are the implications, but I will concentrate on the electroweak sector in this talk only. If you look at the general relativity, and again, my assumption here is that the GR is an effective theory of quantum effective theory. So it can be quantized as field theoretic quantization through the field theoretic quantization, at least in the infrared limit of the quantum theory. And then the consistency of vacuum states in general relativity mandates extension of general relativity to a higher symmetric gravitational theory, which is known as the supergravity. Okay, so the supersymmetry, in our view, is a necessity and necessary extension of Einstein's general relativity from the consistency condition. Now, furthermore, we will argue that a supergravity vacuum is inherently asymmetric and broken spontaneously and by the so-called gravitino condensate, and that means that it also accompanied by emergent fields which form the Goldstone supermultiplets. This is dilaton, araxion, and Goldstino. So now it looks like that this is a very different things, in those two slides, but in essence, these are the reflection of the same phenomenon, and I will try to argue about this. Okay, so I assume that there are students in the audience, and therefore I decided to start with a very simple example, a quantum mechanical example, which shows the subtle properties of the vacua in quantum theory. And the example is a so-called very well-known quantum mechanical problem in double well potential. So we have a double well potential, which can be described by this function over here. And of course, classically, if you think about this potential, there are two states with the lowest energy, which correspond to the position of a particle at each of these two values, okay? And x equal to a and x equal to minus a. And obviously, potential energy here is 0. And if also the momentum is 0, then the total energy is 0. And so that will be the ground state of a particle. So the particle can never move out of this state unless we excited it, of course. So this is these two states are degenerate in energy. They have both 0 energies, and they are not distinguishable locally, but they are stable classically. Okay, But we know that the quantum mechanically, there are always tunnelings occurring through these two states, and you can evaluate this tunneling probability, taking the, for example, initial state at the position -a, the vacuum state, and then evolving it through the Hamiltonian, and finding out whether this appears in the A state instead of -a state. And this probability, quantum mechanical probability, is computing. It can be computed using this so-called path integral. And the path integral, though, is dominated, as you know, by the classical trajectory. So one of the ways of computing this amplitude from transitioning from one vacuum to another vacuum is technically going to so-called Euclidean formulation of the theory, where instead of real time, I will do the analytic continuation of time and consider imaginary dynamics in imaginary time. And in that case, the problem looks like as a classical problem of vacuum rolling, the particle rolling down and back. Okay, so this is so-called bounce classical solutions. So obviously, this path integral dominates by the classical solution, and therefore, in the semi-classical approximation, I can compute the action of this classical path, and that will give me the amplitude of probability. So the amplitude of probability will be proportional to exponent minus quantity known as the action, evaluated at the classical trajectory, as I discussed. And in this particular case, classical trajectory is given by the tangent hyperbolic function. Okay. So this tells us that a vacuum state which classically was stable, say -a at the position -a, is no longer eigenstates of the Hamiltonian, and because of the transition to state A and vice versa. And therefore, if we try to find the true ground state, we have to diagonalize the Hamiltonian. And it turns out that the true ground state here is a symmetric combination of the vacuum state A and the vacuum state -a, which I called a theta vacuum in this case. Okay. So there is some topology associated with these instanton solutions over here. And this topology, which tells you that these solutions are stable topologically by topological reasoning. And it's a zero homotopy group of this solution is given by Z2. And so non-trivial element gives you a hyperbolic tangents, the king solution, and otherwise it's just the trivial vacuum solution. Okay, and so the idea here is that to find the quantum mechanical vacuum of the true vacuum, it has to consider the transition between these two vacua and then compute the minimum energy by diagonalizing Hamiltonian. And it turns out that the minimum energy is satisfied for this theta vacuum, which is a symmetrical, as I said, symmetric combination of these two vacua. Now, this is a prototype example of everything which I will be discussing in what follows, including complicated vacuum structure of Young-Mill theories, gauge theories, which underlies the standard model, and the gravitational theta vacua, which underlies the general relativity. All right, so let me consider now how we construct usually such kind of vacua in more complicated theories, field theoretic, quantum field theories. Let me start with a prototype example of non-abelian SE2 Young-Mills gauge theory. So let me just consider first the pure gauge theory without introduction any meta fields which couple to the gauge fields. And the Lagrangian of this theory, in principle, at the lowest order, contains this term over here, which looks like the Maxwell term. And in principle, relativistic invariance and the gauge invariance allows me to write also the term which is given here in red. So where F tilde is field strength, which is dual to the usual F mu nu field strength, and it's defined like this, where epsilon mu nu rho sigma is a totally antisymmetric tensor. You know, the definition of field strength for the SU2 case is just a generalization of Maxwell's tensor, which contains electric and magnetic fields, the physical observables, and it's given by this expression over here. And of course, since we have a non-abelian case, these fields are matrix valued fields, 2x2 matrices essentially, which are given in the basis of Pauli matrices, okay, which generate SU2 transformations. Now, the difference between these two terms is as follows. So the first term, of course, gives us the generalization of Maxwell's equations in the absence of charges and currents. So these are dynamical terms. Of course, it generates also through the waves, it generates the energy and momentum tensor of the field and so on. This follows from this first term. While the second term, if you look at it, you can express this as a total derivative of a current, K mu, and therefore it does not contribute to the local equations of motions. So it's a topological term. Okay, so local equations of motion and energy momentum tensor doesn't depend on this term over here. So we will be using another expression for K mu through its dual three-form field. So this is a gauge field C with the three antisymmetric indices. It's a kind of generalization of the usual vector potential. And this is a very famous Chern-Simons three-form gauge field, which can be expressed, of course, through the gauge potential of the SU2 Young-Mills theory. All right, so now if you can ask the question that if this term does not contribute to any local dynamics, maybe I can drop it altogether since it does not influence local dynamics. But in fact, in quantum theory, this theta term is mandatory. So you can't simply drop it away. And the reasoning is very general here. So if I want to preserve causality of the theory, and in particular in technical terms, it's known as a cluster decomposition in QFT of product of operators. And so it's mandatory because of that. So otherwise the theory would violate the cluster properties and the causality properties of the quantum field theory. And this is and its results actually from the topological properties of the ground state of the system. Okay, so that there is no way I can remove the theta term in order unless if I remove the theta term, you know, by hand, then I will violate one of those basic properties of quantum field theory. Now, so since this is the theta term appears due to the topological properties of the ground state, let me outline how I construct this ground states first, and what are the topological properties of these ground states. Now, it is convenient in this case to work in so-called Weil gauge, where the knot component of the gauge field are set to 0. And then if I write the solutions, the field configurations for the vector potential is like this over here, where G is the function given here, okay? So which basically element of the SU2 group. Then you can quickly find out that the energy momentum tensor associated with these fields is 0, and therefore this can be regarded, the lowest energy configurations of the field, and the vacuum configuration of the field. Now, one thing you have to notice here, though, is that there are topological properties of this function over here, which is, again, SU2 valued functions. In particular, if you look at it, it gives you a map from the 3-sphere of the configuration space to the manifold, which is given by the group manifold SU2. Now, group manifold SU2 is isomorphic to the 3-sphere as well, and therefore these G's are distinguished by a winding of one 3-sphere over another 6-sphere. So, okay. And these windings are given by integer numbers. So I can wind one 3-sphere around 3-sphere in manifolds, 1 times, 2 times, 3 times, and so on and so forth. Although all these gauge fields will have the same energy, but they will differ by this topological number or winding number. And in a formal mathematical language, this means that the third homotopy group of SU2 is an integer, so it's non-trivial. Now, the topological number n is nothing but the chance Pontryagin number, and it's given by the four-volume integral of the operator f mu dual, which I wrote in the Lagrangian in the first place. Now, in this particular gauge, it can be written in terms of the gauge fields like this, okay? So this number is integer with the proper normalization, and it follows just mathematically from the homotopy group, okay? All right, so if we have these, we can distinguish various G configurations by this particular number n, and so for a given n, I can construct a vacuum state, okay? And so the construction of vacuum state should satisfy the basic properties. First of all, this state has to be a physical state, so it should not depend on the choice of the gauge. It should not depend on the values of these arbitrary gauge functions, alpha A. And the second thing is that it should be a stable state, meaning that it should concern in time, so it should do not tunnel to another state, okay? So there should be a stable vacuum state. Now, the first thing can be achieved naively if I take, for example, all possible gauge field configurations, okay, and then average out over the gauge functions. So I'll take an integral of this, okay? So you may think that in this way, since I average out over the all gauge configuration, I will get the gauge invariant vacuum states, which I will call N. But in principle, the tricky thing here is that this is, of course, true. The states are gauge invariant only if the alpha functions are smooth on the 3 surface, okay? In that case, so-called small gauge transformations, under the small gauge transformation, this state is invariant. However, since alpha can be an arbitrary function, it may have a it may not be as smooth on S3, and if it has some point where it's not smooth, then this configuration is not anymore gauge invariant, but it depends on how many times I wind around this divergent point on S3 of these functions. So under the so-called large gauge transformation, where alpha functions are not smooth, then this particular vacuum state which I constructed is changing by the winding number, okay? So therefore, if I want to construct a fully gauge invariant ground state, I have to take a superposition of these n vacua, which are parameterized by a certain angle theta over here, angular variable theta. And this is a analog of the theta vacua of the double well potential in the gauge theories, okay? So this is a true gauge invariant vacuum of the gauge theories, Young-Mill theories, which is in full analogy, as I said, with the double well potential, which I discussed previously. Now, so the gauge invariance of this theta vacuum implies actually that theta is constant. And that's the different thetas are orthogonal to each other. So there is no transition from theta vacuum to another theta prime vacuum, okay? And so therefore, the Fock space of states, you can have as a disjoint union of the Fock spaces which are characterized by these theta vacuums, vacua. In particular, if I want to compute, for example, the vacuum to vacuum transition amplitude, now we're talking about the theta vacuum over here, this vacuum to vacuum transition amplitude in the presence of external source can be again written down as a path integral, the same way as I did this for the double well potential. It contains the action for the gauge fields, the external source coupling to the gauge field, and you will necessarily obtain the theta term here as a result of just some mathematical identities. Okay, so therefore theta term is mandatory here, and it is mandatory by the consistency condition of the ground state of in Young-Mill theory. Now, similar to double well potentials, we have, of course, a transition between the n vacua, which I discussed before, which are not true vacuum of the theory. And these transitions are mediated by instantons, the field configurations, which are were first discovered by Belavin, Polakov, Schwarz, and Tubkin back in 75. All right. So once we establish this theta vacua, the existence of theta vacua, let us now add the fermions. And the fermions, of course, interact with the gauge field with the gauge invariant way. So all the derivatives which define the dynamics of fermion fields need to be replaced by the covariant derivatives, obviously. And the modification for the vacuum to vacuum transition amplitude in the presence of fermions, it can be written like this. So this red part of it is a result of taking the integral over the fermionic path in the total path integral. So that results in this functional determinant, which depends on the covariant derivative of the fermions in given topological sector nu and generalized mass parameters, okay? So the interesting thing about this, when we add the fermions to the consideration, is that we can prove that the energy of this particular theta vacuum is always positive definite. And this is a proof which comes back in 84 by Waffa and Witten. The key thing about this proof is the two facts. First, that the action, the Euclidean action in Euclidean formulation again, for the Young-Mill theories is always positive definite, okay? And you can also prove that the functional determinant over here, which results from the integration, functional integration of fermionic fields, is also positive definite. And that tells you that, the theta vacuum has the energy, which is positive energy, okay? So the minimum energy, of course, is realized when the theta is equal to 0, and that's equal to 0, okay? Now, if you look just on the gauge theory by itself, theta looks like as a parameter, of the theory, which of course, this term in particular gives you effects of CP violation. Of course, it's a CP violating term, and it contributes, of course, to a certain observables, especially in the strong sector, and this is the reason for the famous strong CP problem. However, the point here is that in pure Young-Mill theory, like, for example, QCD, quantum chromodynamics, this theta looks like just a parameter. However, if I include the gravity as well in this picture, since theta carries, non-zero theta carries a vacuum energy, it carries the energy, positive energy, and we know that under the general coordinate covariance, all types of energy gravitates. So this energy of theta vacuum will gravitate as well. And since this is a positive constant energy everywhere in the universe, it will generate the expanding, exponentially expanding universe, which is known as the de Sitter space, okay? Now, one can argue that de Sitter space, while it is classically stable, quantum mechanically it is not stable. And so all the theta not equal to 0 values of this parameter are incompatible with the usual scattering matrix formulation of quantum gravity. Okay, so that's an important point which I will use later on as my argument. Now, of course, this all is true if the determinant of the functional determinant is non-zero. But of course, this energy can be made 0 if the functional determinant is 0. That means that there is the solutions to this, the eigenvalues of this operator known as the Dirac operator with the 0 eigenvalues, okay? So if there are some solutions of fermionic solutions, which are normalizable and so on, with 0 eigenvalue, then the determinant is, of course, 0 because it's a product of eigenvalues of the operators. And in this particular case, of course, I can say that the theta becomes unobservable. So it's simply, if this probability is 0, this theta term over here is kind of a redundant unobservable phase, which you can remove. Now, the existence of these so-called 0 modes of the fermions in the background of instantons in this non-perturbative vacuum, which we discussed, is directly related to so-called index theorem, as a mathematical index theorem by Atiyah and Zinger, proved in '63. And one way of seeing this is as follows. So if there are 0 modes in the fermionic sector, in this non-perturbative sector, we always have some conserved current related to this. In particular, if we have a massless quarks, for example, or massless fermions, there is a chiral symmetry which is associated with that. And classically, this chiral symmetry is conserved. That means the divergence of the current is 0. However, quantum mechanically, it is not. And this is known as a quantum anomaly. So the divergence of the chiral current or generalized chiral current is non-zero quantum mechanically. And it's exactly proportional to the operator which I was discussing, topological operator. Now, if you integrate this operator, what you obtain from the left-hand side is the difference of chiral charge, which I denoted by Q5 at initial time and the final time. But the right-hand side, as we remember, is related to the topological winding number of vacuum nu, and so it's non-zero. So this tells you that the chiral charge is not conserved, but it's actually an integer up to the factor 2n. And this is related to the difference between the chiral zero modes in this sector. So the fermionic zero modes are mandated actually by the topological index theorem. Okay, so they are inescapable consequence of the anomalous non-conservation of the charges. So what are the implications of these instantons? As I said, the instantons generate transitions between the vacua, and one of the implications of this is that the explicit violation of the Q5 charge, you can find out through the instanton calculus, as it was done a long time ago by 't Hooft. Then there is the emergent explicit violating operators, Q5 violating operators, which describe the specific processes where the Q5 charge is violated. Now, the amplitude of these processes, the strength of the processes, of course, depends on exponent minus action, and action for the instantons, gauge field instantons, you can for the typical nu equal with winding number 1 is equal 8 pi squared over g squared, where g squared is the gauge coupling constant. Okay, so therefore these effects are more prominent in the strongly coupled regime where g is large, and the effects are very small if you are in the weakly coupled regime where g is small, and this suppression factor is large. So these effects are very prominent in the context of the standard model in the strong interacting theories like quantum chromodynamics in the infrared, but they are negligible in the electroweak theory, where the perturbation theory and the coupling constant is very small. However, the key point of our observation was that beside this explicit breaking of the Q5 charge, the very properties of the theta vacua dictate that the Q5 has to be broken also spontaneously. Okay, so again, the Q5 is a charge which is associated with the zero component of the current. And as you know, it generates this U1, anomalous U1 transformations, a change in the phase by this Q5. Now, if you act by this transformation on the theta vacuum, we will immediately understand that the theta vacuum gets shifted. Okay, so instead of theta, you will have theta plus alpha. Now, as I argued before, the consistency requires that different theta vacua are orthogonal, and that means that the action of Q5 on theta, so the Q5 should not annihilate the theta. This means that the theta vacuum should carry certain Q5 charge, and this is the first sign that the symmetry is spontaneously broken. Now, if the symmetry is spontaneously broken as well, that means that there is a particle associated with the degeneracy, initial degeneracy of the vacuum, very light state, which is known as the Goldstone particle. So this is according to the Goldstone theory. In any relativistic system, this is true. So that's a very generic argument of the existence of new particle states in the theory with topologically non-trivial vacuum, like a Yang-Mills theory. Are there any questions? Okay. Yes, please free to stop me if there are questions. Okay. There is a equivalent formulation of this theta vacua through the gauge field theory, or three-form gauge field theory. You can replace this theta term in the Lagrangian by the equivalent term, which now gives, which written in terms of a 4-index antisymmetric tensor field. And this tensor field can be thought as a field strength of the Chern-Simons three-form field, which I introduced before. And in this formulation, of course, this theory is a gauge theory for the three-form field. So the theta vacuum is described as a gauge theory of three-form field, but the gauge redundancy is such big, unlike the electrodynamics, where you have two polarization of a photon. In this case, three-form gauge field does not carry any degree of freedom as it should be in the vacuum. And the key object here is a so-called topological susceptibility, which is a correlator between these topological charges in the vacuum with zero momentum. And it turns out that theta is observable when this topological susceptibility is constant, and it's not observable when this topological susceptibility is zero, of vacuum is zero. Now, in terms of the correlators of these gauge fields, theta is observable if this correlator in vacuum dominated by the pole at zero, 1 over p squared. This is similar to the Coulomb phase of the electromagnetic field, a static electromagnetic field. But the difference is that there are no analog of electromagnetic waves, of course, in the vacuum, and is known as a Lusher pole or the Veneziano ghost pole. And it turns out that the theta, to remove the theta and nullify the theta, theta is unobservable if this gauge field gets Higgsed. So there is a Higgs phase, it's in Higgs phase and develops a mass term over here. Once the mass term is developed, that mass term, that massive three-form field already carries one propagating degree of freedom, which is that pseudo-Goldstone degree for freedom, which I described earlier in a different language. All right, so this is very generic thing about Yang-Mills theories, and now I want to say a couple of things how this looks like in general relativity. So there are few things which are important things which is different in general relativity. First, I based my argument of the energy of theta vacua on the positivity of the action, right, and the energy of the states, and also which is not in general true in general relativity. So neither energy or action is positive definite in GR, and in fact, it's sometimes very hard to define the energy of the system with a full time reparametrization invariance. The second thing is that the eigenvalues of the Dirac operator, which I argued that completely depends on the topology of the vacua, may be affected by the topology of the curved manifold as well, and their causal structure. So curved manifolds are different. They may have boundaries, and therefore the topological features of the vacua can be affected by this. Now, what is the way out? So the way out, in fact, to consider the manifolds that are asymptotically Ricci flat as a vacuum manifolds only. So these are R mu equal to 0. This is a Ricci tensor. And if these manifolds also admit the spinors, so they have a spin structure, you can prove that the action is always positive definite, and also you can define the positive definite mass or energy for these space-times. So this is a famous proof of Schoen and Yau and De Witten back in end of 70s, early 80s. Now, the conclusion then about the ground states of gravitational ground states. So the S is equal to 0, the gravitational action only in two cases. The first case where you have flat space-time, and this with trivial topology, or you can have the space-times which is asymptotically locally Euclidean, and this admits the self-dual solutions for the curvature Riemann tensor, and this is known as a gravitational instantons. So there are topological properties associated with the gravitational instantons. You can take again similar to the theta term and find out that there is a certain type of winding there, which gives for a Gucci constant instanton -1, and the anti-instanton gives a +1. But for the gravity case, beside the theta term, topological term, there is another topological term, which is known as the Gauss-Bonnet term. And for the particular solution, a Gucci constant instantons, it is equal to 2. So similar to the Yang-Mills theory, the gravitational effective action, I should extend. So this is the first term is a usual term of GR, where all the Einstein's equations follow from. I have to extend by theta term, associated theta term, and so-called Gauss-Bonnet term. So this is a kind of analog of the Yang-Mills case for the theta, to the vacuum states of the GR. Now, the interesting thing is that now, if I want to remove the theta term in GR, because they generate positive energy, and the de Sitter vacua, which I argued are not stable vacuum states, then I can try the same thing as I did for the gauge fields, and assume that there are certain zero modes of the Dirac operator for the spin 1/2 particles. But it turns out that for the instantons, or in particular a Gucci constant type of instantons, there are no zero modes for spin 1/2 particles. So you can prove this, and I will give you a proof if I have time. But instead, you can introduce spin 3/2 fermions, exotic spin 3/2 fermions, which has non-trivial index and which can do the job and remove the ground state solutions, theta vacua from the ground state solutions. Now, so that means that to nullify the gravitational theta vacua, we must incorporate spin 3/2 fermions. Now, the spin 3/2 fermions only can be introduced in the theory in a consistent way if we promote GR to a higher symmetric theory, which is known as the supergravity, the supersymmetric theory of gravitation. So this is our argument, just starting from the consistency of GR vacua, why you need to introduce supergravity. Okay, so I'll come if I have time for this, but I don't think I will have a time for the detailed discussions. Now, let me apply this to the electroweak sector of the standard model, this general discussion. So as you know, electroweak sector of the standard model is a gauge theory. It's spontaneously broken gauge theory. So it's SU2 cross U1 gauge theory, which is spontaneously broken down to the electrodynamics. Gauge theory which describes electrodynamics. Now, in the standard model, there is a classically exact symmetry, which is known as a baryon plus lepton number transformation. So it's a rotation of the quarks, for example, and the lepton fields in the standard model. This is in the classical approximation, this is exact symmetry, and it's explicitly broken by quantum anomaly. In particular, the divergence of this current, the corresponding Noether current, is proportional to the topological term, which is associated with SU2 gauge fields and also hypercharge field, okay? SU2 gauge fields of this electroweak gauge theory. And indeed, there are processes in the standard model which violate the B plus L charge by 3 units at least. And this is given by the diagrammatically by 't-Hooft vertex of light. So these are very exotic processes, but these processes in the standard model are suppressed because the electroweak sector is a weakly coupled sector, as I mentioned. Now, from whatever I said previously in a generic term, this setup implies that U B plus L symmetry must be also spontaneously broken. And the order parameter in this case is this local vertex, a Hot vectors, a composite operator which comprising of 12 fermionic states, quarks and leptons. This operator condenses, and the common phase of this operator is the emergent degree of freedom, scalar degree of freedom, which we call eta W. So since I don't have much time, you can demonstrate this explicitly, and we demonstrated this in our work using the toy model of the electroweak sector, which includes the Higgs interaction and so on. And you can demonstrate first that this B plus, under the B plus L, the symmetry and the anomaly implies that there are zero modes for the fermions, despite the fact that the fermions are massive through the Higgs mechanism. Okay, so it's just a topological property and not the property of the local interactions. So if there are these zero modes, and those zero modes were explicitly calculated by Krasnikov, Rubakov, and Tokarev back in '79, then the propagator of these fields in the instanton vacuum, non-perturbative vacuum, can be written as a propagator of zero modes, where the psi naught and psi are the wave function of those modes, and the massive modes here can be separated like this. And then you can go and compute, for example, vacuum expectation value of this composite fermion operator using the instanton calculus. And what happens is that the propagator of zero modes, one of the mu dependence here, exactly cancels the mu dependence of the density of the instanton vacua, so you can get the finite result. So this is just explicit calculation of the vacuum condensate, which happens in the standard model or in the toy model of the standard model. And then you can argue using the Goldstone theorem explicitly that this implies that there is indeed the state which describes this eta W state, which just follows from the Goldstone theorem explicitly. Now, so of course, there are interesting phenomenological implications. You may ask some of them, but the main work are still in progress of how to observe this electroweak theta meson and whether it is possible to observe at all this particle. But the key point here is that the claim of our work is that there is extra particle-like state within the ordinary well-established physics of the standard model. And it's related to the non-perturbative vacuum of the standard model, the electroweak sector of the standard model. Now, let me now quickly discuss the same thing in gravity. So in general relativity, as I mentioned, the problem is that the action is not positive definite. And of course, the quantum gravity here, I understand in a very, very conservative sense, as mediated by the instanton effects summing over the all possible manifolds with arbitrary topology in the Euclidean path integral formulation. Okay, so this is the usual understanding of the path integral formulation. I'm not considering, the string theory or anything like that, since I'm interested in the very far infrared, large distance effects over here, where the ultraviolet divergences are not important. So as I said, there is because of the vacuum structure, the GR action has to be extended by including two topological terms. One term is analogous to the theta term in Yang-Mills theory, and another is again the topological term, which is known as the Gauss-Bonnet topological invariant. Now, as I said, and I mentioned this, that if you take now the zero mass fermionic field, you find out that unlike the Yang-Mills theory, this fermionic field does not have zero modes. And the reason here is that the asymptotic flatness of vacuum manifolds. So the condition that R mu has to be 0 means that the operator here, if I take a square of the Dirac operator, is always positive definite, and therefore there is no normalizable 0 modes except of trivial ones. However, for spin 3/2, you can explicitly compute that Dirac operator is different and they contain 0 modes. I will skip the specific solutions of so there are specific solutions, of course, known for these gravitational instantons. There are interesting effects associated with these, but again, through the explicit calculations, you can confirm that the index of spin 3/2 is non-zero and equal to 2, and spin 1/2 has 0 index. Okay, so therefore, to make the gravitational theta vacuum Weinish in order to satisfy S-matrix formulation of gravity, quantum gravity, you need to introduce 3/2 spin fermions, and that means that you have to extend the gravity to something known as a supergravity. So, and there is more coming in here. So if you have now n equal 1 pure supergravity, for example, the basic field which it contains is a metric tensor, the usual which contains the graviton, and also this spin 3/2 field which gauges a supersymmetry of the action. This is known as a gravitino field. Okay, so these are two propagated degrees of freedom for the pure supergravity case. Then you can argue that in the non-perturbative vacuum, which is dominated by these gravitational instantons, the supersymmetry is no longer respected. And this follows from the fact that if you try to find out whether the supercharges exist, which maintains the supersymmetric transformations, because of the very fact that there are no 0 modes for the spin 1/2 fermions, the definition of these supercharges, which are by themselves is the fermions, you can't define these charges, and therefore in the vacuum the supersymmetry has to be broken. So it has to be broken spontaneously. And this you can verify again from the very generic consideration. It turns out that the gravitino field has this extra anomalous symmetry, U1 anomalous symmetry, which is known R symmetry. Again, you have that the divergence of this anomalous symmetry is proportional now to the topological RR dual term. This is all the same story as comes from the usual Young-Mill theory. And on a very generic ground, you can argue that the gravitino bilinear condensate forms, it's non-zero, and this non-zero condensate breaks supersymmetry spontaneously, necessarily. And as a result, of course, there is a phase which is related to this condensate, which we call R axion, but due to the supersymmetry, there is also breaking of the other symmetries over here, especially the supersymmetry. There are the whole emergent Goldstone supermultiplet, which appears in this theory, which includes the supersymmetric companion of the R axion, which is known as a kiloton, and of course, Goldstino field, which makes mass of the gravitino. Okay, so let me, I think I'm over time now, so let me give my conclusions. So the first thing is to say that, contrary to a widespread belief, non-perturbative quantum gravity effects may have significant phenomenological implication in particle physics and gravity. The generic observation here is that if we have non-conservation of anomalous charge due to the topological features of the vacuum state, especially in the Young-Mill theories, it always supplemented by the spontaneous breaking of the corresponding symmetry. And if there is a spontaneous breaking of the corresponding symmetry, due to the Goldstone theorem, there is a state which is known as a pseudo-Goldstone boson, which has to show up in the particle spectrum of the theory. So this is very generic statement. And if we apply this to the standard model of electroweak sector of the standard model, we predict that pseudo-Goldstone state of the spontaneously broken P plus L symmetry, which is known as which we call electroweak eta W. And in the gravity sector, I try to argue that consistent S matrix formalism requires the extension of general relativity to supergravity. And then that supersymmetry is also broken by the gravitino condensate that results in the states of dilaton, R axion, and the Goldstino. So this is the basic conclusions of this talk, but there are further conclusions which I didn't have much time to discuss. You can have also new type of gauge instantons on the Iguchi-Hansen manifolds, including quantum gravity. And there you can consider, for example, electrodynamics, non-trivial instanton solutions in electrodynamics on curved manifolds, which are not possible in the flat space-time. And there are interesting implications for the spin electric charge quantizations and the existence of unexplored sources of CP violation in the standard model. And of course, you can repeat the same thing in the quantum chromodynamic sector and find out that the solution to the strong CP problem, axion solution strong CP problem, has to be extended in order to have a second axion, which we call the companion axion. And there are interesting cosmological and astrophysical implications of this, which I unfortunately had no time to discuss. Thank you.
Thanks, Archil. That was a really interesting talk. If there's any question, there's no questions yet, but I might kick things off. Did you say, I may have misheard, but could you just clarify? I think you made a comment about the various theta vacua being orthogonal early in the talk. That's not a general property of theta vacua, though, is it?
No, it's a very generic property of the theta vacua. So and it follows from the gauge invariance. So one of the requirement of gauge invariance. So if we have I argued that the theta vacua is gauge invariant. So if you have a gauge invariant theta vacuum with a specific theta, it cannot, it should be stable. So the time evolution should not change that theta. So therefore, the transition to another theta vacuum is not possible. That's the basic property of gauge invariance. It follows from the basic property of gauge invariance. So this is critical claim that the theta vacua are always orthogonal to each other.
And there's no coupling between different theta vacua via instantons or something like that?
No, so the instantons relate this n vacua with the different winding numbers. Yeah. But the theta vacua are defined such a way that they are totally gauge invariant and they are orthogonal with each other.
Okay, right. Okay, that's great. That clarifies that. Thanks. Then you mentioned the introduction of this 3/2 fermions being necessary.
Yes.
What does the introduction of those 3/2 particles have to say about the properties of any spin half particles in the theory? Does it restrict them in any way?
Well, this is a very interesting question, David, which I did not have time to discuss in details, obviously. And this is in our paper given. In fact, if you want the full consistency for the spin 1/2 particles, including the matching of anomalies, then the spin half anomalies related to the gravitational sector should all cancel out. That means that, for example, in the standard model, if you have only left-handed neutrinos, there is a gravitational anomaly which is related to the lepton number violation. So that is not consistent. That means that you have to introduce exactly 3 right-handed neutrinos to cancel anomaly to have a consistent theory.
So
But
it
yes,
has
there
implications
are
for the chiral properties of the spin one.
yes, there are non-trivial consequences of this for the spin 1/2 fermions as well.
That's really interesting. That, I mean, that's potentially quite a important result from this work, I think. The last question that I had to ask you was about, I wrote my notes down here. Oh, yes, you talked about the introduction of gravitational anomalies. I think it was on page 24 or something like that. Does that have any implications or any potential route by means of which we could make any statements about the neutrino masses, for example, as
Yeah. Yes. So I think a few years ago there was this suggestion, actually by our collaborator Giat Valley, that the gravitational instantons and the anomalies, since there is a violation of lepton number, they can mediate a violation of a lepton number. They may be at the heart of, they may be the origin of the neutrino masses. As you know, some type of masses known as the Majorana masses violate the lepton number.
Yeah.
And so the suggestion was that that can be done through the gravitational quantum gravity effects, this non-perturbative anomaly.
Right.
However, this other work points out that there are no such instantons or no such quantum effects in the gravitational sector, since the 0 modes of the 1/2 spin fermions, and in particular neutrinos, are absent. So this is a very generic thing. So there is no direct way of generating neutrino mass if we take into account the fact that topologically those vacua do not carry 0 modes for the neutrinos.
Right.
So yes, so that proposal was presumably incorrect.
Okay.
In that sense.
Okay. Interesting. All right. Well, thanks very much, Archil. Fascinating talk. I don't think there's any more questions in the Q&A panel. I'm just checking. No, there aren't. So let me thank you once again very much. It was a fantastic talk, really interesting. Thank you everyone for attending the seminar. We will let everyone know in due course when the next seminar is scheduled and who's speaking. So keep an eye on your email. And once again, let me remind you, if you're interested, please consider joining the theoretical physics group of the AIP. Thanks again, Archil.
Thank you very much.
Have a great afternoon.
You too.